Hi, my name is Mohammed Tariq, and in this lecture, we will examine some of the applications of binary trees, and more specifically, we will study about Huffman encoding. There are different uses and different applications of binary trees where we use binary trees, and in detail, we will see how Huffman encoding uses the binary tree to reduce the data to compress the data. So let's start this lecture now. We have expression trees. Expression trees also uses binary trees for expressing or for representing the expression. So this point says expression trees and the more general parse trees and abstract syntax trees are significant components of compilers. So binary trees are used by compilers for parsing the expression. So as you can see here, we have an expression. I will not go in the details of this expression and how this tree is formed because my focus of this lecture is on Huffman encoding. So I will quickly go through and I will quickly give you some references that where trees can be used and what are its uses, what different types of uses are there, and how binary tree can be helpful in different scenarios. So for evaluation of this expression, we have this tree. We can form this tree, and as I said, I won't go in much details. So we have formed this tree, and with this tree, we can easily evaluate this expression. Right? The compilers can evaluate such expressions. Parse tree in compiler. So whenever we have an expression, let's say here we have an expression, and then the compiler creates a tree which is here. Okay, this is an example structure, and this is how the compiler forms the expression tree and solves the problem. So in SQL also, the SQL engine creates an expression tree using the query that we write. Let's say, for example, here we have a simple case. Find the titles of the movies with the stars born in 1960. For this, we have a query here, and if this query has one field, is selecting one field, and we have two tables. Then we have a where clause also, and we have a and operator, right? So now, how this tree can be parsed, and how the binary tree can help us in parsing the tree. So here we have a parse tree. So the SQL engine, when SQL engine will evaluate that expression, or you can say that query, it will form a tree something like this. So it's just an example to give you some examples and the uses of binary tree, how the binary tree can be helpful. Now let's discuss about Huffman encoding. What is Huffman encoding? Huffman encoding is actually a compression technique using which we can compress our data, and then we can send the compressed data to the receivers, to other machines, we can say, or to other applications. So data compression plays an significant role in computer networks. To transmit data to its destination faster, it is necessary to either increase the data rate of the transmission media or to simply send less data. So we have two options here. One is to increase the data rate of the transmission media or to simply send the less data. Improvements with regard to transmission media has led to increase in the rate. The other option is to send less data by means of data compression. So this point is actually the our point of focus. So we can compress our data. This is what we can do when application sends a data between two channels. So when we send the data from one location to another, our application can compress the data, and this can be very helpful. For example, we have a sender which sends some data to our receiver. Okay, we have a receiver here. Now the data packets that we send here, that can be, if we can reduce this data, then we can send our data faster. Compression methods are used for text, images, voice, and other types of data. Huffman code is a method for compression of standard text documents. So our text document, or you can say our text data, can be compressed using Huffman encoding. It makes use of binary tree to develop codes of varying length for the letters used in the original message. So Huffman encoding is actually uses the binary tree and then creates some codes of some varying length. We will we will discuss about these codes later. Huffman code is also part of JPEG image compression scheme. The algorithm was introduced by David Huffman in 1952. It's a pretty old technique as a part of course assignment at MIT. We have different other techniques now. We have some other latest techniques available, but right now, for the sake of this tutorial, and we are actually discussing how the Huffman coding is working and what's the technique behind. This to understand Huffman encoding, it is best to use a simple example. Let's now use an example to understand this. Encode 32 character phrase traversing binary traversing threaded binary trees. So we have a phrase traversing threaded binary trees, and we want to compress this phrase. If we send the phrase as a message in a network using standard 8-bit ASCII codes, we would have to send 8 multiplied by 32 equals to 256 bits. We know that in ASCII standard, every character is of 8 bit. Okay, either it's A, B, or whatever. Those all characters are 8 bit. So if we have 30, so total characters in this phrase are 32. So that if we have 32 characters, so the total bits that will be used, it will be 256. Using the Huffman algorithm, we can send the message with only 116 bits. So more than half of the bits have been reduced. How that has been reduced? Let's see. So we have an original text here. We have an original text traverse decided binary tree, and we have 33 characters, which in which we are also including a space and a new line character. So we will count the number of occurrences of characters. For example, let's take T for example, right? Let's take T. So here we have T. So tree A, we have frequency of 3. So the frequency actually showing the number of occurrence of T in this phrase. Okay, number of occurrence of T in this phrase. So now count. This is 1. Okay, this is 2, and threaded binary tree. Okay, this is 3. So total number of occurrence of character T is 3. Okay, let's erase the numbers. Okay, now let's check R. So R is 5. Okay, so now let's check R. 1, 2, 3, 4, and 5. Okay, so the total number of occurrence for R is 5. So we have noted down the frequency. So in this way, we will note down the frequency of every character, and we have also included the space. So the space we have is 3. Okay, the space we have 3 spaces in this phrase. So now once we have the frequency of the number of characters used in this phrase, then we will create a tree. And how we will create a tree? Let's. So here, as you can see, I have a structure here, and I have the lowest frequency characters at the bottom. Then I have 2, right? I have 5. I have 3. So I have 1. So I have arranged these, and what we will do now, we will connect these. For example, as you can see here, V and Y, we have connected this, and we created a node, and we call that node 2. We assign 2 to this node because we have added these two frequencies. We have added 1 plus 1, and the resultant is 2. So what is 2? 2 is actually a sum of these two frequencies. In the same way, we will connect other nodes, and I will call this 2 also. I will connect these two also, right? Now I can connect these two also, and I will call them 4. The new node I will assign 4 to the new node, and then this, and this is also 4, and then I can connect these two, and I can call it 10. Okay, now I can connect these two, right? And what I can call, I can assign 5. Okay, 2 plus 3 to 5, right? Now what I can do is I can connect these two. Okay, and I can 6, I can assign 6. Okay, now I can connect these two. Okay, and I can say 15. I can connect these two, 4, and I can connect these two, say 8, and I can connect these two, and 6 plus 4 is 10. Okay, now I can connect these two, and I can call 18, and now connect these two, and this node will be 18 plus 15 is 13 and 3. Okay, so this is 33. And if you remember, the total number of characters in our phrase, including space and new line, was 33. Okay, let's check, right? As you can see here, the total number of characters we had 33. So now we have connected all these nodes and we got the total number here. So this is a tree that we have to form, and we need to take care that the the root node should be equal to the total number of occurrences of the characters, right? We need to take care of that. So we create a tree something like this. Okay, so now let me show you once again with the proper slide with proper connections. So now we are connecting these two, then we connected these two, then these, then we have 4 here, and we connected these two also, then these two. Okay, and then we have 33. As you can see here, my when I connected the nodes, it was a bit different. Like we have a 19 number here, but in my case, so if you can see here, in my case, I do not have 19, I have 15. Okay, so you can make connections differently, but you need to take care that the total should be equal to the size of the phrase. There are a number of ways to combine nodes, right? I have a note here. There is a number of ways to combine nodes. We have chosen just one such way, and as you to prove this, you just saw the way I connected is different than the one which I showed, right? So here we have some different nodes. We have 9, then we have 19. I've connected different, but the result is the same. Now, once we have connected all these nodes, what's the next step? So next step is start at the root and assign 0 to the left branch and 1 to the right branch. Okay, then repeat the process down the left and right. Now what we are doing is we are actually assigning 0 to the left side and 1 to the right side. The same way we will assign 0 to the left side and 1 to the right side. The same way here, 0 to the left side and 1 to the right side. And we will do this for this whole complete tree. Okay, now we have given numbers to all complete tree. Now what's the next step? The next step is, let's suppose, let's take A. So we will start from the root node, and we will traverse to the A, this way, this way and this way. So A is actually equals to 0, 0, and 0 because we have three zeros here. Okay. For T, for T, the path will be different. The path will be 0, 0, and 1. 0, 0, and 1. Right? So we will concatenate these numbers, we will concatenate these bits, and we will assign that to that character where that character is actually residing. Okay. For let's say for n, the path we will have to take, this is 0, 1, 1, 0. Okay. So for n we have 0, 1, 1, 0. Okay. 0, 1, 1, 0. So this is the path. So as you can see here, we have character codes. Every character has a code now. A has a code 000, B has a code 10001, and that's how every character we have assigned the code. And I've just shown you how these codes have been assigned. Okay, so notice that the first point is, notice that the code is variable length. So the code is of variable length. For example, this is equals to how many bits? 1, 2, 3, 4, 5. This is equals to 5 bits. Now as the space is equals to 3 bits, A is equals to 3 bits. Sorry, space is equals to 4 bits. Okay, space is equals to 4 bits. So as you can see here, there are different bits. E is equals to 3 bits, and G, as you can see, 1, 2, 3, 4, 5 is 5 bits. The second point is letters with higher frequencies have shorter codes. So as you can see here, E E is of frequency 5, but the code is 3. There are only 3 bits used. Now if you see G has 5 bits, but the frequency is very low. Frequency is only 1. So the letters with higher frequency, for example E, have shorter codes, right? They have some shorter codes. The third point is the tree could have been built in a number of ways. Each would yield different codes, but the code would still be minimal. So it says that each will give some different codes. When you form a tree with different connections, we will get some different codes, but code would be minimal. This code would be minimal, as we just seen that when I connected the nodes, those nodes gave us some different numbers, but at the end, the resultant was the same. Okay, now what we have code, we have this code now, and we will send this code to the sender, to the receiver. Okay, with 8 bits per character, the length is 264. With 8 bits, if we send this original text to the sender, so we are actually sending 264 bits. But after applying Huffman encoding, we are actually sending 122 bits, and we it's an improvement of 54%. It's a reduction of 54% of data. So it's an effective coding scheme, compression coding scheme. So up till now we have seen that how we can compress the data and what form it actually gets in, what form it takes after compressing the data. So in the next lecture, we will see how we can send this data, how we can get the original data from this encoded string. I would like to specially thank and I would like to acknowledge Dr. Sohail Aslam for the preparation of this lecture. I have taken help from his videos and presentation slides. Thank you for watching. I will see you in next lecture.